And again, I know we've been here before, but the particular simulation that I'd like you guys to look at, and it's kind of cool. And I've sometimes just used this as a demonstration to just show the class. Which one is it? I think it's this one here. It's charges and fields. There's a whole bunch of different things on this site, but this site's kind of cool because it allows you to do two things. First of all, you can just grab a charge, just pick it out of the bin, and you can measure the you can observe the electric field. If you take two of them, you can kind of see the whole dipolar issue. So what we were talking about with electric dipoles is that you have electric charges that, because of their equal and opposite separation, you get this sort of backwards characteristic looping field. You can kind of just follow them as you stay approximately the same distance away. You can kind of see how they go. So a lot of this stuff you can just sort of see it. I guess you have to take it on the same face value you do me sitting up here squawking at you. But it is kind of cool that. Okay, so it's the whole. I don't want to ask directions or use a map. I'll figure it out, and wherever I end up, I end up. Right? And you can kind of put them on top of each other too, if you really wanted to intensify it a little bit. Yeah, and if you put them a little bit away, you can really kind of see it. So it's kind of cool. Yeah, these are there. Now, so, okay, so you can get rid of them too. And where's that? Now I'm just playing, so I apologize. Oh, there you go. If you click on direction only, in a way it's kind of helpful because you can kind of see the direction of the field as they connect and go around without necessarily needing to look at the different error sizes. Now, though we can go back and forth, so you can explore, it's exploratory. Now, what I'd like to do with this, though, is to consider a couple situations. One of those situations being, we could do this for anything we've potentially ever looked at, but if I put a whole bunch of these things together, and it's going to take a second to do so, I can essentially simulate a line of charge. And in doing so, we can kind of get a sense for how the associated electric field by measurement, and the dirty little secret is that the way the fields are calculated is basically the equations we use. So in a way, it's sort of giving you the equation as a result and then telling you to look at it and therefore come to the conclusion that the equation is the result and therefore your equation works. So it's kind of it's a circular argument that's a little bit fallacious, facetious, something like that. I don't know. Okay, but you can kind of see what it starts to look like as you add these lines of charge that are pretty close to being equal together. You start seeing the symmetries and where the cross terms start canceling out compared to, say, just one charge. So it stops looking like a point charge. I'm trying to put enough in here, so let's see if I get rid of direction only, you can kind of see. Boy, you get rid of direction only, it still doesn't help anything, does it? So I'm just putting a few in here to make it look like a line of charge. And maybe the two things to take away from this that's funny. Saying direction only or no direction doesn't seem to change anything. More speed, less rest, what does that do? Nothing.
The direction only thing,
Just highlights it.
yeah, what it does is, if you have a lot less charge in there, then it kind of shows the color of the arrows fade out as you get further away. But since you have so much charge in there, the whole screen is
Gotcha.
lit up.
So, now I've kind of done something here that is not, I've created a situation where if I wanted to actually show the electric field, I couldn't exactly show it anyway because it goes off the screen. That's nice.
Oh, I see
That's,
there.
that's even more helpful than, okay, at least we have direction again, so why use direction only when I've already got direction there, right? I don't
Try hitting plot.
What's that?
Hitting plot shows a circle around it. Another one.
Which
Down below.
This one?
Yeah.
Well, yeah, but that's showing voltage, not,
Yeah.
the signal, so that's not quite as helpful as I would like, but I wonder if I put some of these up here instead, if I put them as high as I can. There's actually a motivation for this, aside from, oh, look, pretty pictures. Believe it or not.
Oh, there's a lesson behind
Well, I don't know, maybe. Lesson is don't, the lesson of the day, don't bet on the horses. Okay, so I'll put these back up here. Maybe you can change the size of it. Of course not, that was too easy. I wanted to make a line of charge, so I guess we could space them out more, and that would lower the electric field. Maybe do that instead. So, yeah, and actually that kind of helps, right? There we go. There's your uniform line of charge. You get rid of some of them, it kind of thins it out a little bit. And move them up to the top. Want to keep them pretty uniform. A couple things that, oh, there, now we can see, look at that. So, two things I wanted to take away from this. I'll stand out here a little bit so you can kind of see it. So, first of all, first point to take away from this is, and it's kind of obvious when you simplify the equations themselves. I need to get rid of these because these are sort of alternate things. Does that help at all? Let's show the number here. Okay, so there we go. So we can kind of see that if I double the distance, believe it or not, there's a number in there. Maybe I can put a second one here a little bit farther away and kind of see how it's changing. I guess that's the strategy of this. So put them an approximate equal distance away. Try to keep them close to the center. And you kind of see what happens to these guys as you get farther and farther away. Okay, so now, the point then from all of this is that the closer you stay near the edges of this thing, then the better, the more, you kind of see that, that's why I want you guys to look at it, the more the calculations look like you have a direct, cross terms cancel out, and you've got a direct outward normal electric field to your line, relative to your line of charge. But the further you get away, the more these things start to split apart until the point where basically it all starts looking like point charge. As long as you get far enough away relative to the width and the dimensions, everything is point charge far enough away. So that was essentially my goal was to show you, just sort of get a sense for how these things fit together. And it just dawned on me, this is not three-dimensional, so it's not necessarily going to help as much as I would like. But if we were to apply Gauss's law, to a line of charge. I'm pretty sure we did not do this on Tuesday. No, did we? I don't think we did. I think we looked at other things. There's so many different things to look at. Do this all day for just for every possible situation. So we have a uniform line of charge. And here's our charge. I'll use positive just because it's a lot easier to deal with the numbers, or at least the fields point away, and it's a little bit more intuitive, even though we have sort of that idea that everything's about electrons and missing electrons, so in some ways it's more intuitive to have. And let's assume that this thing has a total Q and a length L. Now, as we look at it, it looks like a cylinder, and we can sort of, it begs, we're going to apply Gauss's law to this thing. We need some sort of a Gaussian surface. Again, our application of Gauss's law really starts from identifying a symmetry so that we can apply some sort of a closed surface that will be useful. If it's not useful, then there's no point. Okay, so what might be a useful symmetry to define a closed surface? Well, if you've got a long, straight distribution of charge, then certainly a cylinder is a pretty good starting point. So, say I draw a hypothetical cylinder around this thing. And it's kind of hard with this extra arrow in there. I'm going to try to make it pretty close to symmetric to, or concentric to the center of the line. So, let's say that this has some radius of r. Now, on the surface, that's sort of a reasonable starting point, because you're equidistant at all points, and you've got this cross section at either face that is normal to the plane of the line of charge. Or not the normal, but normal to the direction of the line of charge. Now, we've already solved this problem, and I don't want to describe it off the top of my head, but what does it look like? Go back and look at your results real quick, and I just want a sense of what, from Coulomb's law. Coulomb's law is fundamental too from an empirical perspective. It's just not always useful again. It's not that you can't do it, it's just not always useful. You can't, it's really hard to integrate around a sphere when you're not in some symmetrical location, like when you're inside off-center. It's really hard to integrate over a sphere with a non-constant radius relative to every point. But from Coulomb's law, if you're a certain distance, r, away from a line of charge, this thing has a certain look to it. And I'm pretty sure that there is a Q enclosed. Forget how we defined it. I don't want to derive it, so.
Oh, it's.
Did we express it even for the line in terms of linear density? Okay, good. It's a lot easy when we did. Okay, so we have our linear density, and I know there's gonna be an epsilon naught, and then there's pretty much everything else. There's a pi in here. I know what it looks like when it simplifies, but I want a specific result to start from, to compare. U times R. Okay. It's gonna be 4 pi epsilon naught. R squared. Of course, I'm looking at not a line, a straight line of charge, I'm looking at a circle. Come on now, don't make me derive this thing, because I don't want to waste the time.
Squared
Pretty sure I don't have it in my notes, because I typically.
D squared over
But I can't find it in my notes.
plus D squared over
Find it
2
in your notes?
squared.
Okay.
Plus D squared over.
All right. So, okay, so you have a certain Q total for this line, if you will. And you have a 4 pi epsilon. Then you have a square root of the length squared over 4 plus, it's R, but I'm gonna, or it's L, I use Y, I think, but in general, it's gonna be an R squared, and that's all raised to the 1, to the square root. So in the direction of R, in other words, radially away from the center, we had sort of this result. And the assumption is we're right in the center, and over 2 away from either side. And the results would just differ a little bit if we were on one, if we were a little closer to one side or the other, because the cross terms would not necessarily just cancel out. Now, if we wanted to know, or compare what this electric field is at the same distance r away. So, using Gauss's law. Here's how we might approach it. So again, for this particular example, we might use cylindrical symmetry. So we'll use the cylinder as our surface. Now, if I want to know something about this, and really I'll just focus right here. I don't want to generalize, because what's the difference conceptually between what the field might look like over here somewhere, some distance away from the center between the edges of the line? What might be a concern?
The parts that are symmetrical right now won't be anymore, so. in
Yeah,
the
you'll have
same
an
direction.
imbalance of charge on one side to the other, and so you're going to have, effectively, the field lines are going to look different. So, let's try to stay close to the middle here and just see what we can do. So the problem with, if we look at this sort of on the surface is, yeah, we can draw a cylinder, but if we want to know something about what's going on here, we need to shrink that cylinder so that it's pretty small relative to the length of the line. So I'm going to shrink this thing so that I can make it a lot shorter. The reason I want to do that is I want to limit myself to a range where I don't have to worry over the surface areas that I'm going to be concerned with. I want to kind of stay away from any region where cross terms are going to be not canceling out equally. And if they're not, then the problem is, what am I really looking for when I try to calculate any, or I try to figure out any surface, okay? Primary motivation, we say appropriate surface. Cylinder maybe because it's the right shape, but what is it I'm looking for always? These are always the keys. We need surfaces where either the flux is zero by inspection, right? We want zero flux through some surfaces. I do two things. Either flux over a particular surface is zero, and this can happen, usually implies that E is zero, or doesn't make sense to have A zero, so I'm not, even though that's functionally a possibility. If you're looking for a surface area, any particular surface either must have a zero electric field, which, by the way, implies that the flux is zero, or the scalar product between the area vector and the electric field is zero. In other words, none of the electric field actually passes or crosses over that surface. It skims it and stays flush with it. Those conditions need to be met. To have either of those will allow us to say that over that particular surface, for instance, in the cylinder we've got three surfaces. We've got either face and then we've got the shaft region on the side. The other that we can get away with is pick surfaces where the magnitude, not the direction, but the magnitude of the electric field is the same over every surface. And those are the two fundamental things. The reason is, why are we using Gauss's law in the first place? Really, there's only two reasons to use Gauss's law. If you know something about the flux, so you can calculate it just grandly, then it'll direct you to how much charge is inside. The only other reason to use Gauss's law, other than appreciate its elegance and its beauty in nature, is to find the electric field. And the only way you can find the electric field from one relationship is to have a constant electric field, because otherwise you're going to have one expression with two variables. You're not going to be able to solve it very well unless you start doing more intricate things. So you need to pick surfaces, one way or the other, where we have constant electric fields that are solvable, certainly. So we want a constant E. If E is not constant, then it's a nice esoteric exercise, but getting E as a function of the area somehow is not particularly helpful in most cases. Okay, does that make sense? I mean, that's sort of the fundamental strategy. Okay, so there we go. So that's part of the reason why I'm trying to pick a real thin little sliver here. And I'm going to call it, for now, it's going to look like a calculus problem, but it's really, frankly, not even intended to be. I'm going to call it a dx, if you will. Dx, ds something. It's just the sliver of this thing. In other words, the length is really tiny. Not zero, but it's just tiny enough that wherever I am along here, I can assume that the cross terms are not significant because we're off center. Another way of saying that is make the width of the cylinder small compared to the length of the line. There's another way to express this, and I think the textbook may do this. If it doesn't, you may see this again. Think about the question this way, and it's so artificial I don't really like it, but it's sort of how I learned it. We can calculate the electric field some distance from a line of infinite line of charge. In other words, if we assume that the line of charge is so far on either side, we can neglect any of the cross terms because they all cancel out because it's too long relative to where we're looking to know. Kind of like G is 9.8 wherever we are, as long as we're near the surface of the Earth. So that's sort of the idea, but really what it means is you just make the sliver tiny relative to the length of L. So yeah, we're pretty close to the center in this case. All right, so there's our sliver slice, and we have a surface area here that is related to the radius that's at the distance that we're looking at R. Now, we approach Gauss's law to this. We've got a closed surface that has an aggregate surface that has three different faces. So three specific surfaces. We've got the face on the left. With the face on the right. And then in between those, we have the side region. So we just got to calculate the flux for each of these three regions, add them together, and they'll be equal to the amount of charge that is enclosed by that surface. Again, it doesn't make any sense to calculate Gauss's law over the whole charge if this is our surface, right? The charges that produce the flux that we evaluate are only the charges that are inside the surface. Okay, so for each of these faces, we're going to have a flux. We'll call it flux 1. Flux 2, and flux 3, where the total electric flux, now we evaluate these over areas.